This is the main result for this section. Let A be a square matrix, then the following statements are equivalent. The reduced row echelon form of A is equal to the identity matrix. A is a product of elementary matrices, and A is invertible. That means if any one of these is true, they must all be true. They essentially mean the same thing. They are different ways of expressing the same core mathematical idea. All right. Now to prove these, we're going to go in a cycle. We're first going to show that if A is true, then B must also be true. Whenever A is true, B is true. Then we will show if B is true, then C must also be true. And then we'll show that if C is true, then A must also be true. And once we do that, we complete the cycle. And so if any one of these is true, they all must be true. Okay? So that's the plan. Let's start by showing that if A is true, then B is true. All right? So suppose the reduced row echelon form of matrix A is equal to the identity matrix. Now, we know we can get to the reduced row echelon form of A by applying elementary row operations to A. And based on what we know about elementary matrices, that's the same as multiplying by elementary matrices, right? Then we can transform A into the identity matrix I using elementary row operations. Let E1, E2, all the way to EK be the elementary matrices corresponding to those elementary row operations. Okay? Then, if I take the first matrix E1 and multiply by A, that's the equivalent of applying the first elementary row operation, right? And then after I apply the first elementary row operation, I apply the second elementary row operation. So E2 times E1 times A is what I get after applying 2 elementary row operations. I keep doing this until I apply all the elementary row operations. Okay? Once I'm done applying all the elementary row operations, I'm going to get the reduced row echelon form of A, which is equal to the identity matrix. Okay? But all these matrices here, they're all elementary matrices, which means they all have inverses. So let's multiply both sides by the inverses of these matrices. Multiplying both sides of this equation by the inverses of the elementary matrices gives us, so on the left-hand side, I had what I had before, but I want to multiply by the inverses of these elementary matrices on the left side. Now remember the socks and shoes property. When I multiply by the inverse of a product of matrices, that's the equivalent of multiplying by the product of the inverses, but with the order changed. So the furthest inverse on the right would correspond to the furthest elementary matrix on the left. And so I just swap the order. And I know, since these are elementary matrices, they all have an inverse, so I can multiply all these together. Okay? But of course, what I do to one side of the equation, I need to do to the other. All right? Now, all of these matrices multiplied together, they all undo each other. So I just get I, the identity matrix, times matrix A, which means I'm just going to get A on the left-hand side. On the right-hand side, I have all of these matrices times I. But of course, a matrix times I is itself, so the I will go away. Showing that A is just the product of the inverses of those elementary matrices that we need to get it into reduced echelon form. Remember, the inverse of an elementary matrix is an elementary matrix, so we've done what we needed to do. We have expressed matrix A as a product of elementary matrices. Okay, so part one's done. We have shown that A implies B. Okay, next let's show B implies C. If A is the product of elementary matrices, then A is invertible. Suppose matrix A is the product of elementary matrices. Say that means we could write A as the product of elementary matrices, E1 times E2 all the way to EK. All right? But again, we know that these matrices have inverses. So multiply both sides of the equation. By the inverses of the elementary matrices. To obtain so on the right hand side, I could multiply EK inverse to E2 inverse to E1 inverse times E1, E2 all the way to EK. And on the left hand side, I'm multiplying by the same thing. Okay. On the left-hand side, of course, these give me the identity matrix I. And so I get EK inverse, E2 inverse, E1 inverse, times matrix A must be the identity matrix. All right? So now we have two square matrices that multiply together to give me the identity matrix. That must mean those two matrices are inverses of each other. Which means A is invertible. Okay? So we have shown that B implies C. If A is the product of elementary matrices, then A is invertible. Finally, let's show that C implies A. If A is invertible, then the reduced row echelon form of A is equal to I. Suppose A is invertible. Then if we transform the augmented matrix with A augmented with I into reducer echelon form, we obtain this augmented matrix where I is on the left side of the augmented part and A inverse is on the right side. Okay? But what this means in particular is if we're applying, if we're transforming this into reducer echelon form, that means we're transforming this into reducer echelon form. Okay? And it is transforming into matrix I, which proves the result. All right? So all three of these are different ways to say the same thing. If the reducer echelon form of a square matrix is equal to the identity matrix, then we can write it as a product of elementary matrices. Okay? And it therefore also must be invertible. All invertible square matrices, you can write, the reducer echelon form of it is the identity matrix. It's the product of elementary matrices, which means the only matrices that we can't write as a product of elementary matrices are those matrices which are not invertible, where the reducer echelon form of the matrix is not the identity matrix, where we would have some free variables to the homogeneous system of equations if A was the coefficient matrix.